So we're already on level 2.3. 2.3 covers properties of functions. So these are interesting phenomena that happen across a range of different functions, and it's mostly examining the patterns. We also are going to cover one subject that you are definitely going to see in calculus next year, and that's talking about average rates of change for functions and not just lines. So we're going to start this off by talking about the evenness or the oddness of functions. So for a function to be even, this means that if I plug in a negative number for x, I'm going to get the exact same thing if I plugged in just a normal x. We've seen something like this before, and when we covered symmetry. So what does this mean symmetrically? This means that any even functions are symmetrical about the y-axis. The one that we should be the most familiar with, y equals x squared, our standard parabola, is a mirror image over the y-axis. And that's what it means to be even. Something, if I plug in a negative number, I get the same thing if I just plugged in a normal number. So if we have even functions, the other type of functions that we find interesting are odd functions. And odd functions means that if I plug in a negative x, it will be the exact same thing if I plugged in a negative f of x. Or if I plug in a negative for x, I'll get the exact same thing as getting a negative y value out. Now we've seen this before too. Even so, with odd functions, they're symmetrical about the origin. And the common one that you've seen before, if we wanted to say f of x equals x cubed, that means I have one side up here and the other side down here. If I plug in a negative x, it's like getting a negative y value back out. We're symmetrical about the origin. So these are really common things that happen with various different functions, and then we're gonna examine in this level. So first off, determine if a graph is even, odd, or neither. And so we say neither even or odd, we just write neither because it doesn't take that much to write, or it takes too much time to write even nor odd, so we just write neither. So we look at A. A is going to be even. If we look at B, well, it's not the same reflected over the y-axis, and it's not the same reflected over the origin. So we write neither. And then for C, we can look at this, and it's definitely not even, but if we folded this over the origin, we're going to get this to be matching up. If it's symmetrical about the origin, it's going to be an odd function. So an even function, this one's neither, and this is odd. So 2, what if we aren't given a picture? How do you tell if something is an even function or an odd function or neither? And so this is the same thing. Also determine if the graph is symmetric with respect to the y-axis, the origin, or neither. So first off, f of x equals x squared minus 5. Now, we could know what this graph looks like. It's just shifted down 5, and we have our standard parabola. And if we know what this looks like, this is going to be even. How do we test? Is if we can plug in a negative x value, and we can check if it's symmetrical about the y-axis. Well, if I plug in f of negative x, I just get x squared minus 5, and x squared minus 5 is just f of x. So we get here the definition that we had all the way at the top. If I plug in a negative x, I get the same thing back out. So let's try the same thing for b, x cubed minus 1. So this is obvious. We're going to first plug in f of negative x and see what happens. So f of negative x is the same thing as negative x cubed minus 1. Well, if I cube a negative x, I get negative x cubed minus 1, and that's f of negative x. And that doesn't look like an even function. I didn't get the exact same thing back out. And I want to also see what negative f of x is equal to. Negative f of x would be negative x cubed minus 1, or negative x cubed plus 1. So I can look at f of negative x, and I can see that it's not equal to negative f of x. And so I can come to this conclusion, and I just proved that this is symmetrical. It's not even, nor is it odd, so it's a neither function. And in fact, if we remember our translations, which we'll get to in a little bit, this is an x cubed graph just shifted down 1, and since it's shifted down 1, we don't get any nice symmetries that we had before. So for the last one, for C, how about 5x cubed minus x? So I'm going to do the exact same thing. First, I'm going to plug in a negative x into my function. So that gives me negative x cubed minus a negative x. So that's 5. That's going to be a negative 5x cubed plus x, and that's the same as negative x. I can obviously see that it's not the same as f of x. So what I do want to figure out is, what is negative f of x? Well, that's just going to be negative the whole thing, which I think I'm on to something. That's going to be a negative 5x cubed plus x. That's negative f of x. So we just showed that f of negative x equals negative f of x. And because this is true, that means that this is an odd function. So, moving on to the next page. The next bit of information that we want to know about a function is where something is increasing and where something is decreasing. So this is oftentimes what throws people. For something to be increasing, we list the x values where the y values are going up. So we can look here, this first problem says, where's this function increasing? Well, we can look and see that from negative 4 to 0, my y values are going up. And that's the only spot where we're going up. So if I wanted to write this interval for where this is increasing, I can write brackets, because we're including negative 4, and then all the way up to 0. We're going to include that point, because it stops increasing at 0. Likewise, if I wanted to define decreasing, it's going to be a similar definition. We list the x values where y values are going down. So again, we're going to list the x values that tell us where to look for our function. So where is this going down? Well, I can see from negative 6 to negative 4, and then also from 3 to 6. So I'm going to write that as my interval from negative 6 to negative 4. I'm going to include that because we just stop, and we can get more specific as to if we include this point or not. And then we're going to say union. Remember, this is, again, union, which means we're combining two intervals that are spaced out. And then we're going to say from 3 to 6. So that's our interval where we're decreasing. So the last one, it says, where is it constant? So if we have something that's constant, we list x values where the y stays the same. So we're looking for the y to be constant. So where is the y values constant? In this function, from 0 to 3. So from 0 to 3, we have a function that's constant. Now you might look at this and say, hey, we can't have these overlapping intervals for each section. And that's exactly why we use parentheses, because at some points we're not including these. So is this function increasing, decreasing, or constant right at 0? Well, it's hard to tell. So that's why if we wanted to list these and be more specific, we would use parentheses. Next up, definitions, which are kind of important. These are going to be basic definitions for a local maximum and a local minimum. This is the highest point in a given window or range. And likewise, the local minimum is the lowest point in a given window or range. And I want to be specific about why we're using these terms local maximum and local minimum. Well, figure 21, which is in the next example that we're going to do, is perfect to illustrate why we use local. The opposite word is global. So you can see, where is the local maximum? This function goes up to infinity on either side. So technically, this doesn't have a highest point. But if we look at this range right around the origin, we see that we have some interesting stuff happening, and we can examine that to find out where the local maximum, which the plural for that is maxima, and the local minimum, or minima, if we have multiple, are going to be. So looking at this graph, where is the local max? The local max for A is at this point, 1, 2. This is where the highest point is in this given window. For B, what are the local minimum or minima? Here we have 2 lower points. We have 2 minimum, so this is our max. And here are our mins, our local mins, is -1, 1, and 3, 0. If we wanted to be super specific, we would call -1, 1 the local minima, and we would call 3, 0 the global minimum, because this is the lowest point that our function will ever be. Next up, list the intervals where we're increasing, list the intervals where we're decreasing, and if we had any constant, we would. So increasing, where are we going up? So where are we going up? For this, we're going to be using parentheses. So from -2, at our minimum, -1 right here, all the way up to 1, we are increasing. So from -1 to 1, we are increasing. At 1, we stop being increasing. So that's why we do not include that. And so this is where we're going to be more specific about this. And then we're going to include the next range from 3 off into infinity. 3 to infinity is where we are increasing. Likewise, we can look at where we're decreasing or going down on the y. So from -infinity to -1, we are decreasing, we're going down. Then from 1 to 3, we are also decreasing from here to here. So that's how we list off increasing and decreasing intervals. For D, what is our domain? Well, our domain is all of the numbers because there's no restrictions here. So we can write all reals or all reals. Spell that right. And our range, what are our possible outcomes, our outputs, is, well, the only restriction here is we have a low point of 3, which we can't go below. So because we have a minimum at 3, and that's our global minimum, we can be 3, and then we keep going up from there. So 3 to infinity in interval notation. We got one more page, and then we'll be done with level 2.3. Looking at example 5, it says, using your graphing calculator to graph this function from -2 to 2. So let's just pull up our graphing calculators. I already have mine on, and let's try and keep that glare away as much as I can. I have mine on the home screen, and I'm just going to hit this calculator button really quick. If you're at this scratch pad, I can hit this button one more time, and I go to my graph. If you don't already have one, you can hit tab to type in the equation. Just to save time, I've already typed this in. So what I want to do is hit menu, and I want to go to window and zoom, because it also tells me to restrict my x's from -2 to 2. And once I hit enter, I can see my graph looks a little funky. So it's asking me, if you can't read this on the paper, approximate where the local maximum and local minimum are located. Well, I know that this is going up, so I want to increase my window just a little bit on the Y to see what this looks like. So I'm going to again go back to window, and I'm going to go window settings, and then I'm going to go change my Y's, and let's just zoom out just a little bit. Let's say our minimum value is -20, and our 20, just to be sure that I can see this graph. So now I get a clear picture of what I'm dealing with. So to find a local maximum, again, we're going to hit window, and then we're going to go to analyze graph, which is number 6, and we're going to look for a maximum. So to find a local maximum, we go and set our lower bound, so we drag our mouse over and you click, and then an upper bound. All we want to do is highlight the highest point, click, and then click one more time. And we can see that at this point right here, at -0.816, comma 11.5, we have our maximum. So I'm going to write that down on the piece of paper. I highly suggest you do the same. So our max is going to be -0.816, comma 11.5. So to calculate our minimum, again, we go to menu, we go to analyze graph, we go to minimum, which is 2, then we go left of it, then we click, we go to the right, click, and then we can see we're at 0.86, comma -1.583. So I'm going to write that on our piece of paper. 0.816, comma -1.53. So looking at where our graph is increasing to decreasing, we'll be increasing, if we can keep this on the page, increasing up to our maximum, and then we'll be decreasing down to our minimum, and then we'll be increasing past it. So if we know, and we have, let's just zoom out just a little bit, we have our max and our min, we are going to be increasing up to our max, so from -infinity to -0.816. And then we are also increasing past our minimum, so 0.816 off to infinity. And where our graph was decreasing would be from negative 0.816 to 0.816. So that's increasing and decreasing, and that's using your graphing calculator. Last thing, super important thing, average rate of change. So this is just like slope. Change in y over the change in x, or the difference in the y values over the difference in the x values, and we don't want to look at the same x values. So find the average rate of change for this function, 3x squared, from 1 to 3. So what we want to do to find the average rate of change is it's delta y over delta x. So I'm just going to write it out. It's f of 3 minus f of 1, that's our y's, over 3 minus 1. We'll just plug in 3, which is 3 squared times 3, which is 27, minus 3 all over 2, because 3 minus 1 is 2. So that's 24 over 2, which is 12. Now what happens if we increase that interval from 1 to 5? Well, the delta y over delta x, change in y over change in x, is now f of 5 minus f of 1 over 5 minus 1. Or 25 times 3, which is 75, minus 3, all over 5 minus 1, which is 4. So I have 72 all over 4. And if I have 72 over 4, that's 36 halves, which is 18. So my rate increased a little bit. Last one. What happens if we go from 1 to 7? Which again is f of 7 minus f of 1 over 7 minus 1. So we're given 7 squared times 3, which is 49 times 3, which is 147 minus 3, all over 6. So I have 144 divided by 6, and 144 divided by 6, which I do, is going to be 24. So my rates aren't constant if I'm looking at this. And if I look at the graph, that's going to be a skinnier parabola. So the first lines that I checked were here, and then the next lines I'm looking at here, and I'm looking at their slopes. And the third lines I'm looking at are more like these ones. So obviously the slope is getting steeper. And that's kind of the study of calculus, is finding out where rates are changing. So the last thing, example 7. Find the average rate of change of g from negative 2 to 1. So let's first do A. Find the average rate of change. So that is f of b minus a. So it could be f of, let's do the far one, f of 1 minus f of negative 2 all over 1 minus a negative 2. So that average rate of change, or that slope, f of 1, we're going to plug in, is 3 times 1 minus 2 times 1 plus 3. So 3 minus 2 plus 3, which is 4. And then we're going to do negative 2, which is 3 times negative 2 squared, which is 3 times 4, 12. Negative 2 times negative 2, which is 4 plus 3. So that's 16, 19, all over 3. So if I did that right, and I just noticed that I had the wrong sign, so it's 4 minus 19 divided by 3, which gives me negative 15 over 3, which is negative 5. So once I get negative 5, that's my slope. The next question says, find the equation of a secant line. A secant line goes through a function in 2 spots. And a secant line is going to have the same slope as the average rate of change. So we already found the slope, and now we have 2 points. Well, if we think back, how do we write the equation of a line given a point and a slope? We're just asking for point-slope form. So y minus y1 equals m times x minus x1. Well, what we can use is, I think the easier one is using 1. So let's do y minus 4 equals negative 5 times x minus 1. Is that the equation of a line? Yep. And that's all we need to do to find the equation of a secant line. And that's your first intro to calculus material that you'll see this year.